So before we start, I upload the second homework number 2 to Lima. Okay. So which is start today. Just don't forget that. The next several classes we will discuss different type of special concretes. Okay, we call that high performance concrete or HPC. I think we have 4 classes from lecture number 15 to lecture number 18. Okay. Here shows one of the example, a so-called cement car. This is the cement cross-linked with polymers, but majority of the cementitious materials is still cement. Okay. The tensile strength very, very high. So 200 megapascal is higher than even the compressive strength of many high-strength concrete. Okay. So that's the reason why they can make a car using cement, because the tensile strength is so high. So this type of concrete is called micro defect free or MDF cement. Okay. Using pressure to remove large voids and entrapped air, and also I believe the fibers is also used to make the concrete stronger. Research history of HPC. From early stage, the focus will be on how to achieve the highest strength possible. Okay. Today, we also use a lot of high-strength concrete, for example, in high-rise building, where the strength of concrete is very important. Okay. And then some other type of performance become more focused on, such as durability or focus on French property of concrete, okay, such as SEC. For high-strength concrete, the goal is, of course, focus on how to enhance the strength as much as possible. Okay. This is useful for high-rise building, because by using higher strength concrete, we can reduce the cross section of the concrete, so we can reduce the dead load of the building. Okay. But as we mentioned before, high strength is not equal to high durability. Okay. Some very old concrete may not be very strong as today's high strength concrete, but they can last hundreds or even 1,000 years. Okay. If a high strength concrete have some durability issues, they cannot last long. For example, for concrete has high drying shrinkage or high autogeneous shrinkage, even though the cement paste are very strong, but shrinkage will cause a lot of crack. Okay, so that will not make the high strength concrete not very durable. If the focus is on high fresh properties, such as self-consolidating concrete, and then it can also be qualified as high-stress concrete. Okay, so SEC will be one of the concrete we talk in future lectures, but this is a type of concrete which can flow under its own weight, and it can pump over a long distance, and it can flow into every corner of the formwork. It is useful, especially when we have a very congested rebar in the formwork. Okay. Okay. So I try to play some video for us. We'll see if we can play that. me see. Okay, sorry, the video for some reason doesn't work. Okay, so I will see how we if we can play next class. Okay, so this is a video for SCC flowing easily in the formwork, even with very congested rebar. Okay. So to design high performance concrete, depending on what type of performance we design, either high strength or high durability or high flowability. So whatever, we should focus on processing technology, the property of the raw materials and the final products, and property based on chemical analysis and the nano and microstructure analysis of the concrete materials. Here compare conventional concrete, high-strength concrete, and a so-called ultra-high-strength concrete, depending on the strength level. Okay. We can see the water-cement ratio are quite different. Okay. And some of them use chemical admixtures such as superplasticizer to achieve the high strength, because without superplasticizer is very hard to achieve a very low water cement ratio and fully compact the concrete. Silica film and flash are very commonly used for high strength concrete. Sometimes also use fibers to enhance the toughness. Okay. We will have a lecture covering fiber reinforced concrete later this semester. Okay. And we may also even heat treatment and even pressure to achieve the ultra high strength performance. Okay. So here shows the stress and strain curve of ultra high strength concrete compared with normal concrete. Okay. The strength is very high. The slope, which is the E value, for high strength concrete is higher compared with normal concrete. And also we can see high strength concrete tend to be brittle, which means after the peak load, it will fail suddenly compared with normal concrete, which has much longer post-peak behavior. All right. So this is what we discussed, the crack behavior for normal concrete. We call that crack localized. Okay, so that is the cracks opens up in a certain location, not all of the location. Okay, and in other part of the concrete, even after the peak load, the concrete can still resist some of the load. Okay, that's why we have the post-peak behavior. But for high-stress concrete, all the components in the concrete are very strong. So when crack occurs, they tend to propagate all through the concrete. So not too much post-peak behavior. So high-stress concrete behave more similar to cement paste or mortar compared with traditional concrete. So this is one of the early project around 2008 to 2009. I did before I joined UH as the assistant professor in 2011. Okay, so around 2 or 3 years before I joined UH. This is one of the project. We design ultra high stress concrete, also has fiber in it. Okay, so the concrete need to be strong enough to resist the high speed heavyweight truck impact. Okay, and also the concrete need to be durable enough to resist the harsh marine environment. Okay, this is one of the security barrier in San Francisco Bay Area. Okay. So we use particle packing series trying to achieve a very dense matrix, not only for aggregate but also for the powder system. Okay, which means cement and silica film system. Okay, focus on rheology, behavior using the admixtures and the fibers, and also study the cement chemistry to ensure the hydration product is strong enough. Okay. So the end result is ultra high strength fiber reinforced concrete with compressive strength more than 200 megapascal, very high fracture strength, and very, very low chloride diffusion rate, which means the concrete will be very durable also. Okay. I'm not sure if I can play the video. The video seems not work today. Okay. So we have some video clips. Hopefully I can play that next time for you. This is the prototype test with Sand F750, which is 50 kips truck traveling at 50 miles per hour, impact on the concrete barrier, which will serve like a so-called street furniture, okay, something like that. So we have some plant on top of the concrete barrier. People can sit on it, but actually it's a very, very strong security barrier, can stop the truck within 3 feet or 1 meter. Okay. So this is some of the picture of the impact. Okay. Okay, so this is the aftermath of the impact, the debris from the truck, the engine oils, but the concrete itself is very good. So actually after the first impact, we did a second impact for another truck, which impact concrete barrier on the side. Great. The next part of today's lecture is a borrow from lecture from Professor David Lan. Is I think currently the ECI president, okay, and he is a professor from University of Illinois. He was my co-advisor for my PhD study. Okay, so this is one of his lecture on designing or production of high performance concrete. So basically, how can achieve a strong and durable concrete? And you will see many of the information in this lecture. We know that already. Okay, so but it's a very, very good review on designing high performance concrete. So HPC design principles. For hardened property, we need to focus on very strong matrix, okay, which means the cement paste need to be strong enough. The interface means the ITZ, or interfacial transition zone. And also, of course, the aggregate. Okay. The porosity control the permeability. And also the connectivity of the pores is also a big factor controlling concrete permeability. Okay. And we know concrete permeability is very, very important for designing a durable concrete. And volumetric stability, which means the creep and the shrinkage of the concrete should also be well controlled. So that is hardened properties. For fresh properties, the workability should be at least acceptable. Okay. For concrete with very low water cement ratio, it cannot be very, very flowable, but it should be at least workable, which means we can fully compact the concrete. Okay. The setting time should also be acceptable depending on the requirement of the engineers. Okay. So that is controlled by the type of cement, the particle size, or the fineness of the cement, or what type of admixtures we put in the system. And also the rate of strength gaining. That is controlled by the type of cement. For example, type 3 cement, we call that high strength cement. So the set time and the strength gaining speed will be faster compared to type 1 cement. Temperature, of course, is very important. Higher temperature, the strength gaining will be higher. Set controlling admixtures, retarder, accelerator, all will control the strength gain. How we can improve the strength of concrete? We have many methods to do that. We can improve the strength of cement paste, or the ITZ, or the aggregate. Remember the weakest link series. So this is the three major components in concrete. So we need to improve the weakest part, okay, depending on many factors. If the weakest part is the cement paste, okay, we should improve that. Okay. If the weakest part is ITZ, we should improve ITZ. So for the cement paste, it could be modeled as single phase solid. Okay, the strength of the cement paste is depending on the porosity mostly. So which is the P here. So the lower the porosity, the higher the strength of the cement paste. So the main problem is how we can reduce the porosity, okay, and how we can avoid larger pores, and how we can refine the size of the hydration or the grain. Okay. If we can reduce the inhomogeneities, okay, reduce the size of the interface, reduce the size of voids, okay, so that's we can reduce the major issues. The role of water-cement ratio. Okay. The water-cement ratio is #1 factor controlling the strength of concrete. Okay. Higher water-cement ratio, lower strength. Lower water-cement ratio, we have higher density, we have higher strength, but the setting time will also be shorter. Okay. So keep that in mind. And also we have higher temperature due to higher heat evolution. And the workability will of course be lower. So that's why for high strength concrete, we need to put a superplasticizer in the system. So that is cement paste. And then let's look at the ITZ, which is the boundary between cement paste and the aggregate. Okay. So ITZ is typically weaker if the water cement ratio is high, so higher than 0.5, okay, then we could have micro cracking in the ITZ due to dry shrinkage or thermal contraction. Okay. So here said aggregate plays no role until water cement ratio is less than 0.5. Okay, so that means when the water cement ratio is high, the weakest link is in the ITZ or the cement paste. So that's why aggregate plays no role. So when the ITZ and the cement paste is strong enough, or stronger than the aggregate, then it will play some role to control the strength. Okay. And the aggregate need effective stress transfer. Okay. So without a strong ITZ, the stress from the cement paste cannot transfer to the aggregate. Okay. For cement, optimum fineness. The smaller the particles, that is good for strength, but too fine, it is bad for rheology, okay? Because we need more water to mix the cement paste. Smaller particles, the surface area is high, so we need more water to achieve the same workability. If we can reduce the amount of C2A, we could avoid some setting problems. Okay. And a higher percentage of C3S and C2S, we can generate more CSH and improve the strength of concrete. Okay. And here it says ESTM types are not optimized for high performance concrete due to high percentage of C3A, but that probably not something we can control. For mineral admixture, such as fly ash and slag, so we know pozzolanic reaction transfer calcium hydroxide into CSH. Okay. That is due to one, the so-called failure effect, okay. Because the Portland cement, the size is around 110 micrometer, and silica film is around 100 times smaller. Okay. So silica film can fill the gaps between cement particles. Flash is more spherical shape. It can increase the workability of concrete. Slag is more angular shape. The size is also similar to cement particles. Okay. And here shows the so-called ternary diagram. Basically, the percentage of silica oxide, calcium oxide, and alumina. Okay. Depending on the source of the powders, such as the slag, class C flash. Okay. So how we can look at the percentage? We can just, for example, class C flash, we draw a parallel line, so parallel to this line. Okay. So intersection of the line with calcium oxide. So that is a percentage for oxide. We can also draw another parallel line like this. Okay. Intersection with alumina will be the percentage of alumina. Okay. And pay attention to the arrow. So here, the percentage of aluminum oxide is 0, and here is 100%. And we draw another line parallel to alumina. The intersection of that line with the line of silica oxide is the percentage for silica oxide. Okay. So from there, we can read the percentage for different raw materials. For silica film, the common dosage is around 3 to 10%. Sometimes we can use 15 or even 20%. Okay, but if we use too much of silica film, that will cost us a lot of superoxidizer. Because silica film is very fine particles, we need a lot of water and the superoxidizer to achieve a workable concrete. Okay. Okay. The particle size for silica film we know is very small, but it may stick together. We call that aggregation. So that will make the effective size of silica film very large. Okay, sometimes even larger than typical cement particles. So that will impair dispersion or even generate ESR. Okay, because silica film has a lot of reactive silica. Okay, so aggregation of silica film, it may just act as the reactive aggregate. So pay attention to that. So here shows silica film densify the ground mass, which is the one type of CSH, the hydration product. Okay. So the picture on the left shows the paste was with water cement ratio of 0.4. Okay. We see a lot of black, so that is voids. But with 10% silica fill, the same water cement ratio, we see much denser matrix. Okay, because we see much less voids, which is the black color. Okay. For flash, the common dosage is around 15%, but we can use a much higher percent for now. Okay, even 100%. If you remember the guest lecture from the Visa Tuesday this week, we can use up to 100% of flash. But the quality will varies by source. Okay, flash is a byproduct of coal burning process, so we need to care about the quality control for flash. Okay. It will increase the setting time and also reduce the early age strength of concrete. The cost of flash typically will be lower compared with cement, but that is depending on the where you talk about. For example, here in Hawaii, the cost of flash is much more expensive compared with cement, about twice as expensive as cement, because we do not produce quality flash here in Hawaii. Okay. So for slag, remember slag not only has pozzolanic property, but also hydraulic properties. That means slag can form CSH without cement. Okay. But slag needs some type of alkali to activate its hydraulic property. Okay. Slag is from the steel producing process, so its availability depending on where you have a steel plant. Okay, so common dosage around 15 to 30%, sometimes even 60% or even 70% by weight of cement. Again, we should be control the quality of slag because it's a byproduct. Okay. Here, talk about the dosage of superprocessor. Okay, so show different type of cement. If we increase the dosage and measure the flow of the cement paste. Okay, so what we can see is we increase the dosage initially. The flow time will be lower, which means the slump become higher. Okay. However, beyond a certain point of dosage, further increase superprocessor, there's no change in flow time. Okay, so that means at a certain point, we have fully saturated cement paste. So we call that saturation point for superprocessor. Okay, so beyond that point, it just wastes more superprocessor. Okay, it will not increase the slump. Here shows the role of retarder. Okay, so this is the time. We have high strength, high performance concrete with superprocessor and with superprocessor and retarding agent. Okay, so we can see with retarding agent, it will extend the rheology. We have longer time for higher slump. So the slump loss is smaller. So we have more time to work on concrete. It will also reduce the amount of heat, reduce the temperature. And then let's look at the third component, which is aggregate. Okay. So improve the strength of concrete. May be important and may not be important. Okay, and here just this strong aggregate has these properties. Okay, and the size of the aggregate will affect the strength of the concrete, as we know of, and also the porosity. And for aggregate, we should also eliminate the potential for ASR, okay, or for freeze-out damage. The freeze-out damage from aggregate, we call that decracking. That is due to porous aggregate. And also abrasion for weak aggregate. And here are some of the comments for gradation requirement from ASTM. Okay. And for high performance concrete, we tend to use smaller size of aggregate. One, we can increase the strength, but because smaller size, we also increase the surface area of aggregate, so workability will be reduced. For shrinkage and creep or volumetric stability, the source of cement and the mix design are very, very important, especially water to cement ratio. Good curing can reduce thermal shocking, reduce temperature increase, and thermal cracking, and also reduce autogenic shrinkage and drain shrinkage. Okay. So curing is very, very important. Longer the curing time, the better to reduce shrinkage. And here shows one of the example of using saturated LWA. This is lightweight aggregate, which is aggregate with very high porosity. Okay. We have another lecture talking about lightweight concrete, which is the concrete use lightweight aggregate. Okay. But for lightweight aggregate is very light because it has a lot of pores. Okay. If we saturate the lightweight aggregate, it will working as a water reservoir to slowly release water into the concrete and reduce the potential for autogenic shrinkage. Okay. From a lecture of shrinkage, we know for concrete with very low water cement ratio, it is very hard to control autogenic shrinkage. Even we have a lot of curing, because the cement is very dense. Water from outside cannot release the drying of the pores due to hydration. Okay. If we put saturated lightweight aggregate, because the aggregate is everywhere inside the concrete, so it will effectively reduce the autogenic shrinkage. So for high strength concrete or high performance concrete, the rule of thumb is we use lower water cement ratio, if possible, use flash, silicon fuel mass slag, use superplasticizer if the workability is a concern, and we should use higher cement content to compensate for the lower workability. Reduce the size of aggregate, also use high strength coarse aggregate, and use the larger size of the sand or fine aggregate. But the cost will be higher because of these materials. And based on the cost and the strength, we can kind of optimize the cost. Okay. As shown in this table, this shows dollar per cubic yard of concrete, and the other curve is the cents per PSI per cubic yard. So that's consider both the strength and the cost of the materials. Okay, and we can see we have a lowest cents per psi per cubic yard of concrete. So that is probably the optimized the cost. Okay. For optimized for both the cost and the strength of concrete. And here shows two mixed design for normal and high strength concrete. Water cement ratio is quite different. Okay. The strength also very different. For normal concrete, doesn't have a flash and silica film. Okay. And also for high strength concrete has less amount of aggregate. So HPC I is the mixed design for normal concrete. And we know it has limitation when we talk about how to design normal concrete. Okay. For example, we assume water cement ratio and air content are the only issues that affect the strength. Okay. And assume the maximum size of aggregate, water content, air content are only issues for affect the slump. Okay. I think we discussed this when we talk about how to design normal concrete in lecture number 10. Okay, and doesn't consider mineral admixture at all and any chemical admixtures at all. Okay. And doesn't really consider different type of cement admixtures. Okay, so to design high performance concrete, basically we cannot use HPC I-211 method. Okay. But the committee from HPC I also gives some guidance on design high performance concrete. Okay. But just we cannot use HPC I-211, the design method for normal concrete. Okay. Right. For high performance concrete, we know the slump is controlled not only by water, but also by superplasticizer. Okay. And the water cement ratio, not only factor for strength, but also silica film and flash. Both of them are not considered by HPC I-211. Okay. So the mixed design is basically optimization problems. We need to optimize by considering many factors. Okay, not only strength, not only shrinkage, but also cost and other factors. Okay, so we need to decide the water cement ratio, the size, gradation of aggregate, type of cement, and how much of cement we use, type and dosage of admixtures, both mineral and chemical admixtures. Okay. Look at water cement ratio. Reduce the water cement ratio, we can densify the matrix, disconnect the pores. That's good, okay? Because it will provide durability by reduce the porosity. It will also increase the strength. Okay? But it will also decrease the workability and decrease the setting time and increase the hydration heat. Okay? And also potentially increase the autogenesis shrinkage. Okay. For aggregate, smaller, well-graded coarse aggregate is stronger. It will also improve the packing density of aggregate, but it will increase the demand for water because we have a smaller particle size, higher surface area, so workability will be lower. Okay. For cement content, if we increase cement content, it will generate more higher strengths. Okay, because for the same water cement ratio, we have a better workability and better compaction also. Okay. But higher cement content, you will increase potential for thermal cracking, okay, and also increase dry shrinkage and autogeneous shrinkage, because only cement case will shrink, aggregate will not shrink, and also, of course, the cost will also be higher. Okay. For mineral mixtures, silica film will increase the strength. Cost will be much higher. Silica film is 10 times more expensive than cement. Workability will also be lower because the particle size is small. For flash, it will increase the strength, reduce the cost, improve the workability, but delay the strength gaining speed. If you want higher early age strength, you cannot use flash. For superplasticizer, it will increase workability, so we can allow a lower water cement ratio. It is essential for high strength concrete. Okay. Dosage, how much you use, it is very sensitive. And slump loss, which is loss of slump of concrete over time. Okay. So that's potential concern when we use superplasticizer. Okay. And also sometimes we have a so-called compatibility problems with cement and other type of admixtures. And
on the last slide, just a reminder, why is it fly ash reduces strength?
It reduces the strength gain, which means reduce the early age strength. The final strength will be higher.
Oh, so it just takes longer to get
longer,
the strength.
Yeah, take longer.
Okay. And why is that? It just it slows the reaction, or
because post-dynamic reaction is slower compared to cement.
Oh, okay. Okay.
Yeah. Okay. Thank you for your question. For retarders, it will reduce the heat, okay, and extend the setting time. But again, potential compatibility problems. When you combine different type of admixtures, always check if they will interact to each other. Okay. And dosage is very, very important. Okay. Too much retarder, the concrete may never set. Okay. And what time you add retarder is also important as one of the problems in the first meter, right? Delay 10 minutes, the time adding the retarder, you may increase the effectiveness of retarding agent. Okay. ACI 211 does give some guidance to design high strength concrete. Okay, this is ACI 211 4R. This is the first revision, the year 93. So right now they must have a current version. Okay, so design high strength concrete with Portland cement and flash. Okay. And the ACI 333 R is revision, year 92. Okay, again they must have a current version for that. State of art on high performance concrete. Okay. And we also have some other mixed design method, just listed here. This is the name of author. If you are interested, you can search. Okay. Then let's look at the production or the quality assurance and quality control issues for high performance concrete. Okay. So including curing, performance-based specs, team coordination, assurance, and the potential problems we see from the field. Okay. We just quickly go over that. Okay. For curing issues, for water cement ratio lower than 0.45, put more water is the best, or the water additive approach. Okay, because for concrete with lower water cement ratio, we better provide more water to the system. Okay, to ensure it doesn't have too much shrinkage. Okay, and the water cement ratio is too low to complete the hydration. Okay. And here says the long-term effectiveness is questionable because the pores is very small and the close off, which means the permeability could be very low. So curing may not be very effective. If you can do, we can do ponding, which is providing layer of water on top of the concrete. Okay. And longer curing, the better, the denser microstructure. Okay. The same concrete at 1 day, a lot of pores. 28 days, we see a lot of hydration product. Okay, emergency alert. Okay, today these days I get a lot of flash flood warning. Okay, just be careful, drive outside. Performance-based specs. High-performance concrete is very sensitive to small change. Okay, one mix design does not fit for all. Okay, so it is best to specify properties and allow the engineers and the material supply to adjust, and also the contract to adjust based on the performance requirements. Okay, and try to do a lot of try mixes. Okay, and verify in the lab and in the field before the actual usage. Okay, so for example, we try to design some STZ for state of Hawaii. Everything is good in the lab, but in the field, because SCC is very sensitive materials, small changes in gradation of aggregate or moisture content, you may suddenly see the performance of SCC is not good at all. Okay, so keep that in mind. Okay. So team coordination between the supplier, engineer, the contractor are actually very, very important. Okay, so that's true when you start working. And assure quality of stock materials. Okay, we should check if the materials comply with the specs. Okay, and if it's not, we should allow time to do the correction. Okay. And be cautious when we change the source of chemical admixtures. Common problems with fresh property of high performance concrete. Okay, because we tend to use a lot of superplasticizer, we will have higher slump loss. Okay, or low effectiveness of vibration. Okay, because the concrete may be very sticky due to low water cement ratio and a high percentage of silica film, for example. Or the concrete is very sensitive to water content. Okay. And the setting time may be very long if we use flash, or we use retarder, or a lot of superplasticizer. Okay, shrinkage, bleeding, plastic shrinkage, especially may also be a problems. Okay, so vacuuming is recommended. Okay. High-strength concrete may tend to be sticky because, again, low water cement ratio, flash, and silica fume will make the concrete sticky. So finishing could be a problem. Okay. Not finishing, sorry. Temperature and strength monitoring. Okay, so high heat of hydration could be a concern due to low water cement ratio and higher amount of cement. Okay, and high early age thermal cracking may be the result. Okay, so to compensate that, we can use retarding agent to slow down the hydration, or we use flash or slag, or we can even reduce the temperature of aggregate by adding ice into the mixing water. Okay, so this is a common practice during the summer concreting. Okay, and high performance concrete will obey maturity laws. Okay, so if we monitor the temperature change using thermocouples to track the heat, so we can relate that to the strength gain. And here you can talk about how and when we test the strength of concrete. Normally we check the strength at 28 days, okay? But because we may use silica fume or retarder or flash, so 14 days or even 7 days sometimes is also required. Okay. If we use flash, we may check the strength at 2 months or even 3 months because hydration will be slower. You could also different size of cylinder, different materials for the cylinder. All this will affect the result a little bit, okay, but that will save us some problems. We can do more tests for different days. Okay, and here says different curing process or even the caps and condition may affect the strength difference between the test result from the lab and in situ strength. And here give us some of the typical mix design for high performance concrete. Okay. So strength at 28 days, okay, from 65 to 120. Okay, sometimes the strength will achieve 145 at 3 months. So this is all belong to high strength concrete. Okay, some of them are even ultra high strength concrete. Okay, so they use different approach, flash. Some of them use silica fume, different type of admixtures such as retarder and superplasticizer. Okay, different water to cement. C plus M means cement plus mineral admixtures, silica fume, flash, or slag. Okay, so water to cementitious materials is around 0.25 to 0.37. So that is typical range for high performance concrete. This is another sample mix design for precast concrete. And that's the result for high performance concrete. So 11.7 KSI at 2 months. Okay. Very durable concrete, very good freeze-thaw resistance. Okay. Shrinkage acceptable and very, very low permeability. Okay. So this is our first introduction lecture for high performance concrete. Here is the list of books, show the authors, different type of mixing eye for high performance concrete, and also the website from Federal Highway Administration, National Institute of Standard and Testing, and other website, okay, for high performance concrete. The next 3 lectures, we're going to talk about different type of HPC, including SCC, fiber reinforced concrete, polymer concrete, lightweight concrete, and so on. Okay, but that's it for today. Okay.